Let's look at the physical, chemical, and biological properties of stereoisomers. So in general, enantiomers are going to have the same properties unless they are actually interacting with something that's chiral, because they have the same polarity. And diastereomers have different polarities, and so they also have different properties. One of the type of properties that we look at, physical properties, pardon me, is the optical activity of molecules. So let's look at a couple of brief videos on that. Here's one.
A beam of light is composed of electromagnetic waves that vibrate in all possible directions perpendicular to its path. Certain materials, such as plastic Polaroid film, have the property of absorbing all the waves except one that vibrates in a particular plane. Light that consists of waves vibrating in only one plane is referred to as plane polarized. Chiral compounds interact with plane polarized light, rotating its vibration plane to the left or the right. Therefore, they are referred to as optically active compounds. Two enantiomers of the same compound will rotate the plane of polarization through the same angle, but in opposite directions.
All right, so that's one of them. That's a little bit of an introduction to this idea of optical activity. And now let's look at another brief video on an example. I'm sorry things kind of keep showing up in the screen. Hopefully you can see around them. That's one of those annoying things about YouTube. They're always advertising about other videos.
We can measure the optical activity of Caro syrup using a laser and two polarizers.
We first adjust the second polarizer until no light gets through to the screen.
When the neck of the bottle is inserted, the light is rotated as it passes through the syrup, and so some of it gets through the second polarizer to the screen.
We then again adjust the second polarizer until no light gets through.
This shows that the light is still linearly polarized, although it's rotated as it passes through the Caro syrup. When the light passes through 2.5 centimeters of Caro syrup, it's rotated through an angle of minus 30 degrees. And when it travels through 6 centimeters of syrup, it is rotated through an angle of minus 76 degrees. And when the light passes through 9.5 centimeters of syrup, it's rotated through an angle of minus 118 degrees. In fact, the angle of rotation is proportional to the distance of syrup through which the light travels.
Different wavelengths rotate polarization by different rates, as can be seen by placing the bottle between these two polarized sheets.
All right, so that optical activity is dependent upon concentration of or path length through which you are going. The light is traveling through your chiral compounds. It's also dependent on wavelength. In general, enantiomers, remember, are going to be similar. They have equal and opposite activities. So if you have one enantiomer, it's going to rotate your light in the positive direction. The other enantiomer will go in the negative direction. And if you have a solution of equal amounts of enantiomers, one will rotate in the clockwise direction, one will rotate in the counterclockwise, and they cancel each other out. And overall, you get an optically inactive solution. And we call that a racemic mixture. So here's an overview of some physical properties that go back to that idea that enantiomers are going to have really similar properties, diastereomers not so much. And so melting point, you can see, are the same, solubility is the same, optical activity is equal and opposite, and then this is the racemic mixture on the right, and then there's just a little bit about naming down here. Now, because enantiomers have the same polarities, they actually are they're pretty difficult to separate. And when you do a chemical reaction, unless you use a chiral environment, which we'll get to in a minute, you're going to wind up with a racemic mixture in the end. And so if you only want one of those enantiomers, you're going to have to use something like chiral column chromatography to separate or resolve. It's sometimes called enantiomers. And a chiral column has a little bit of its silica gel with a chiral component stuck on it, and it hydrogen bonds. And you can see, if you can imagine what the other enantiomer would look like, it wouldn't stick as well to the hydrogen bonders, the amine and the carboxylic acid down here. Those would be opposite, and so you wouldn't end up getting, or you would end up getting a different RF value, and they would be separated on the column. So chemical properties of stereoisomers, enantiomers, because they have the same polarity, are going to react the same, and you're going to get an equal amount of the product unless you start with something that's chiral, or you sometimes have or somehow have a chiral environment. So, for instance, in the reaction at the top, you end up, the reactants here, you have two different enantiomers, you wind up with the same product, it's the same rate, it doesn't matter. Down here with substitution, you actually start with a chiral compound, and so you're going to end up with a chiral compound as well. So if you do have something that's achiral as a starting material, but you want to make something that is chiral and you only want to make one enantiomer, then you have to use some sort of environment or catalyst that is chiral. And indeed, this is what your body does with its enzymes. So for example, this is the Sharpless epoxidation, and there is a chiral reagent you can see here, and it actually holds the reagent, it actually holds the starting material, which is an alkene, in the correct conformation, so that it only gets an oxygen on one side of its alkene, and you wind up with a single enantiomer as a product. So when you're doing these chiral reactions, or reactions that are catalyzed by a chiral catalyst, you can measure the relative amount of your enantiomers with an equation called the enantiomeric excess. And what you do is you plug in the observed activity. So for instance, in this scenario that's in your book, the observed activity was discovered to be minus 45 degrees. And then the pure enantiomer has an activity of minus 53. And so you end up, when you divide one by the other, you get 85%. And so to interpret that, or what that means, is that 85% of the product is adrenaline, or what was the single enantiomer which the chemist was trying to make. And then that other 15%, we just can't see it in the optical activity. And the reason is that it is racemic. And so it's 50% of the adrenaline and then 50% of the enantiomer. And so you divide that 15% by 2, you get 7.5% of each enantiomer. And so if you add 85% and then, which we know is the adrenaline, and then 7.5%, which is half of that racemic mixture, you wind up with 92.5% of the adrenaline, and then there's 7.5% of whatever's the other enantiomer. So as I was saying, this is really similar. These chiral catalysts are similar to what happens in the body, because in the body, your receptors, your enzymes are all chiral, and so enantiomers will react differently in the body. One way that you've probably experienced before is if you've smelled caraway seeds and spearmint. Carvone is what you're smelling when you smell caraway, and arcarvone is the odor of spearmint, but they're just enantiomers, and your nose has chiral receptors, and so they do interpret these odors very differently. There's also, as far as pharmaceuticals go, enantiomers of pharmaceuticals will behave very differently. And I encourage you after this to go to the Wikipedia page, which is linked on the page for this lesson. And here's an example. Thalidomide was sold in the 1950s and 60s in Europe. It was not sold in the U.S. Because it was actually blocked by the FDA, and particularly Frances Kathleen Oldham Kelsey, who was a pharmacist at the FDA, and she recognized that it hadn't been tested on mothers or on pregnant women, although it was being prescribed to pregnant women to treat morning sickness. And so she thought that there wasn't enough evidence that it was safe, and it turned out that although one enantiomer is actually an anti-nausea drug, the other one is a teratogen. It causes severe birth defects, and so there are many children born between 1956 and 1962 with severe birth defects from the enantiomer of the active drug, or the drug that does what we want it to do. The hard thing about this is that this is a labile carbon, meaning that it actually racemizes in situ. It actually, if you start with R and you let it sit around, you'll eventually get some of the S as well. And so there's no way to safely prescribe thalidomide and just use the anti-nausea drug because it will eventually become the teratogen, just as it equilibrates. And so it can't be prescribed to nursing mothers, it can't be prescribed to pregnant women at all. And it is, however, used as a drug to treat other diseases.